Larson, who again almost didn't make it, but is here, is a research associate at Northwestern University, where he is the associate director of CIERA, which is the Center for Interdisciplinary Exploration and Research in Astrophysics.
CIERA.
CIERA.
Geologists should be able to say that.
Yeah, I was just hesitant. So he works in the field of gravitational wave astrophysics, specializing in the fields of compact stars, binaries, and, not the least of all, the galaxy. So he works in gravitational wave astronomy with both ground-based LIGO project, which is here about here this evening, and in the future, we hope, I will add, space-based detector LISA. It hasn't been funded yet.
It is funded in Europe.
Oh, okay.
And the funding line in the U.S. is in place.
Yeah, okay. Maybe next. Shane grew up in Eastern Oregon, was an undergraduate at Oregon State, where he received his BS in physics in '91, received a PhD in theoretical physics in '99 from Montana State University, just up the road. He's an award-winning teacher for the American Physical Society. He's also an avid amateur astronomer, and Mike Adler here will talk with him about that. Observing with two home-built Dobsonian telescopes named Equinox and Cosmos Mariner. He currently lives in the Chicago area with his wife, daughter, and cats. In addition to astronomy, he enjoys hiking, mountain biking, geocaching. You have to come back on Sunday.
Yeah, I know, right?
He also collects Legos, fountain pens, and telescopes. He currently lives, and I read that he contributes regularly to the public science blog at WriteScienceWordPress.com and tweets with the handle @ScienceJedi. J-E-D-I.
That's it.
So without further ado, please join me in welcoming our speaker tonight, Shane Larson.
Thank you, John. And thank you, everyone, for being here. I gather it's a little bit more snow than you were expecting, but I'm certainly glad you all came out and take the opportunity to spend the evening with us. So I'm an astrophysicist, and the more you get to know me, in 10 years when I come back, you'll be used to this at this point. You'll find that I'm one of these people who very deeply believes that everything in science is deeply intertwined and interconnected. Whether it's geology, which all of you are invested in, whether it's biology, chemistry, or as it turns out, astronomy. They're all part of the great endeavor to try and understand our place in the universe, where we came from, and what our part in this big story is all about. And so tonight I'm going to tell you just a little bit of that story, the part that I study, which is about astrophysics and about the frontiers of astrophysics. This really is the bleeding edge of what we're able to do. And so it's been a remarkable time to be alive and practicing astrophysics, to live through the discoveries that I'm going to tell you about. It's something that we've anticipated for a century now. And when you first start in astronomy, it's those things where you're like, wow, wouldn't it be cool to see? And here we are, we've seen it. And so it's a really fantastic story, and one that I'm very pleased to share with you. As we go along, you will undoubtedly have questions. So please, if you do not hesitate to ask. I will answer them as we go along. That almost certainly inspires your neighbor to ask questions as well, but so I'll try and control them as we go along. Okay, but if you're really confused, please ask, because almost certainly someone else is confused too, and we want everyone to go along with the story with us. Okay? At the end, I'll take questions until John drags me out. Okay? Okay. Now, invariably, what will happen is 2 weeks from now, at about 2 in the morning, you'll wake up and be like, oh, I wished I had asked Larson this. Okay? Do not wake up your spouse. They do not want to talk to you about astrophysics at 2 in the morning. Okay? But my email address is here, and it's here for a reason. Okay? s.larson@northwestern.edu. You send me an email. I'll send you off to read some stuff. I'll try and help you find the answers to the questions you got. Okay? My blog, I write lots there about all kinds of astronomy and astrophysics. There's a lot there about our topic tonight, gravitational waves, so you're certainly to go there. How many of you are on Twitter? Anyone live tweeting right now? Okay. If you're live tweeting right now, there's my handle. You can certainly tweet at me. I'll answer you on Twitter as well. There's stuff at my YouTube channel as well. Okay? Okay. So I'm going to tell you about this new area of astronomy called gravitational wave astronomy. This picture that you see on the title screen is by a very famous artist named Mark Garlick. He's actually an artist and a physics professor at Warwick in the UK. But we often use these pictures because the things that I'm going to tell you stories about tonight are things that we will never see in the kind of detail you can see in this picture. They are too dim, they are too far away, they are so exotic that we've never been able to resolve them the way you're used to seeing pictures in textbooks and in the news and so on. So we resort a lot to artist renditions like this, but I'm going to tell you the story behind what goes into this. And the reason we use Mark's art is because Mark's a physicist, and so Mark tries to get the picture right. But it's still an artist rendition. But let me tell you what we know and how we know it. So tonight we'll start with how we see the cosmos. I'll remind all of you about some of the things you know about astronomy. I'll tell you a little bit about the great machines that we've built to do this type of science, the gravitational wave detectors themselves. And then at the end, we'll talk about the discoveries, the things that we've learned and what we hope to still learn with this new branch of observational astronomy. So, anytime you pick up a newspaper, you turn on the news, you open up a book about astronomy, these are the sorts of things that you see. Especially for those of us who grew up during the space age and in the age of Hubble, we have learned about the cosmos through pictures like the ones on this screen. And it's truly a testament both to the power of our machines, the power of our technology to be able to capture images like this. All of these are real images. But also a testament to our ability as a species to transmit these images so widely and so broadly to our civilization that there's very little on this screen that looks unfamiliar to a room of random people that I don't even know. What's this up here in the upper left? Moon. Okay, what's that right below it? Yeah, and what's that? The great red spot. Okay. Okay. Oh, well, that's another story and an entire talk, right? Okay. What's this? What's that? Lightning. Not lightning. Aurora. It's aurora, right? Okay. It does, yeah. So it's Jupiter, right? What's this? The Andromeda Galaxy. See, some of you even know which galaxy it is, okay? What's this? The Bubble Nebula. Amateur astronomers over there. Okay. What's this? The Veil Nebula. And this is? A globular star cluster. Okay? And what's this? That is the Milky Way. Okay? Now, those of us who live in the West and grew up in the West, that is something we're used to seeing. If you just walk out at night here, get just away from the city lights here in Jackson, you'll see that, especially in the summer. Okay? In Chicago, I have people who have never seen this, and they think that's an artist's rendition. Okay? And this is one of the great difficulties that we struggle with, is that our civilization is becoming very urbanized, and we are losing that connection to nature, both directly, the sorts of stuff you have by being able to walk out your door here, but also through the night sky, the sorts of stuff that you see on this picture. Okay? Now, all of this we've been able to discern and learn about through the application of a single piece of technology called the telescope. Without the telescope, none of this would be known. How many of you have seen the moon? How many of you have seen the moon through a telescope? Okay, tell me some things you know about the moon. It is made of cheese, yeah. Tell me something you don't.
Meteors hit it.
Meteors hit it and created craters. What else do you know about the surface of the moon?
Expelled from the world.
Oh, yeah, okay, so that's a long story, the creation story of the moon. But yes, currently the best guess is it was created in a collision with Earth. What else do you know about on the surface, though? It has seas, or maria as we call them, large basaltic plains. Okay? It has a far side, which we from Earth often call the dark side, but it is not always dark, but it has a far side. Okay? It has mountains, it has craters, okay? It has highlands and rays coming out from the craters. Okay? All of that stuff you cannot know and you cannot see with your naked eye. If you go out and you look at the moon with your naked eye, all you will see is it's round, it changes its phase, okay? And it has light spots and dark spots. There's not a single crater, there's not a single ray, there's not a single mountain or canyon you can see on the moon without the aid of a telescope. And this is the story of modern astronomy. Everything that you and I know, that we take for granted, is because we're able to build technology that can do more to observe and discern the universe than we can with our native senses. And it began with the telescope. And the story I'm going to tell you tonight about gravitational wave discovery is part of that continuing application of technology to probe everything we can about the cosmos. Okay? So, telescopes work with light. Okay? And if you spend any time at all looking at astrophotographs, you will see a picture of this region of the sky. This is a very famous region of the sky. Does anyone know what it's called? Amateur astronomers? So this is called the Rho-Ophiuchi complex. Okay? It is near the bright red star Antares, okay, in the constellation Scorpius. This is the heart of the Scorpion. Okay? This is one of those globular clusters that we saw there at the beginning of the story. Okay? But in the background here is all of this illuminated gas and dust. And if you look at this region with your eye, even through a telescope, you won't see anything except the stars and that globular cluster. The color that you see here is through the application of another piece of technology called photography. That someone somewhere along the line had the wherewithal to take a camera and stick it on the side of a telescope, and it revealed bits of the universe that we never had any idea existed. Now, I show this picture because it very accurately captures what the job of astronomers has been for 400 years. You and I, just like every professional astronomer, is confined to live here on the surface of the Earth. A few of us have been to orbit. Are there any astronauts in the room? Okay. All of us have been confined to live here on the surface of the Earth. Okay? And everything that we know about the universe has been learned solely by looking. Never by going out, gathering samples, doing experiments, nothing. All we do is look. And so for 400 years, we've gathered light, not unlike the light you see in this picture. We've gathered it into our instruments, we've captured it on film, and we've extracted from that light all the knowledge that you know, that you've been taught, that we have about the cosmos. Light is an extraordinary messenger because every object that emits light encodes in that light stories about what it is and what it's doing. It tells us about its composition. It tells us, is it moving? It tells us, is it spinning? It tells us its temperature. All of that information is encoded in the light, and if we capture it in our telescopes, we can discern all those things that we think we know about the cosmos. But it's not easy. Okay, so let's pick this star right here. Okay, this little green star right here that's underneath the globular cluster. That star is behind everything you see in this picture. So the light from that star encoded the size of the star, the temperature of the star, how fast it was spinning, the mass. It got tossed out into the universe, and that light is speeding across the cosmos, carrying the story of that star and its life. But along the way, it passes through all of this gas and dust in this picture. And so when it gets here to Earth, you and I, the astronomers, looking at that spot in the sky with our telescope, get a mixed bit of light. Some light from the star, some light from the gas and dust. And the stories are tangled together. How do I know which temperature belongs to the star and which temperature belongs to the gas? How do I know which chemicals belong to the star and which ones belong to the gas? That's our job as astronomers, is to disentangle that story. But it's not easy. Light is not very faithful at telling us stories that are easy to disentangle. But that's what we do. Okay? So this is the story that astronomy is still doing and will continue to do. But for 400 years, this has been the tale. Now, there's certain difficulties with this. Not everything in the cosmos can be seen with light. Okay? So, Dim stars. What's the brightest star in the sky?
Sun.
Ah, there you go, the sun. Okay, so I know it was a trick question. You all hated that in science class, right? Okay, the sun is the brightest star in the sky. Why is it bright? Because it's really freaking close to us. If I took the sun and I put it on the other side of the Milky Way galaxy, there is maybe only one telescope on Earth that could detect it. The sun is intrinsically not a bright star. It's actually really dim. And in fact, most stars in the galaxy are not unlike the sun. When you and I go out and we see the Milky Way arching over our head, we're not looking at the light of individual stars, we're looking at the combined light of 400 billion stars together, all shining light, some dim, some bright, but mostly dim. But together they make something we can see. And the sun is like most of those stars. It's intrinsically dim. There are stellar skeletons, which we'll talk about, which emit almost no light. When stars die, they stop giving off light that is easy to see. And so if we want to study those stellar skeletons, doing it with telescopes is hard. Black holes. By definition, black holes are objects that don't give off light. So if your method for studying the cosmos is to use an instrument that gathers light, a telescope, then you are never going to be able to study an object like a black hole. Now, you should be out there going, well, wait a minute, Larson, because every 2 weeks NASA announces that they've discovered the largest black hole ever known. Okay? And that's right, they have. But they're not looking at the black hole itself. They're looking at the black hole doing stuff to other things. Right? You come in, John's wearing a cast on his foot. And you're like, what happened, John? And he's like, my snowblower threw me down my driveway. You didn't see the snowblower do it, but you saw the evidence of what the snowblower did to him. It broke his leg. This is the same game we play in astronomy. We don't see the black holes. We see the evidence of what they're doing to other things in the cosmos. Dark matter and dark energy make up 97-ish% of everything in the universe. Dark matter is a substance that emits no light. It has gravitational influence on the things around it. In particular, it makes galaxies spin faster than they should. I've just told you everything we know about dark matter. But people still write big, fat, 500-page PhD theses about this, okay? But literally, that's all we know about dark matter. It's been a mystery since the 1930s, when Fritz Zwicky made the first detection of its existence, and we still don't really know what it is. Okay? So, it doesn't emit light. If telescopes are your only game, then you're never going to be able to detect dark matter. Okay? So what's an astronomer to do? Lots of the universe is no good to be observed with telescopes, at least not directly. Well, as it turns out, everything on this list, everything on the previous list, everything that you've ever heard about, moves and changes under the influence of gravity. And that's really the story that I'm going to tell you tonight. The idea that you could observe the cosmos with gravity itself was one that Albert Einstein stumbled upon. In 1915, he proposed and put forward what we now call general relativity, a modern description of the way gravity works in nearly all physical situations we've ever encountered in the universe. And as a consequence of that, in the following year, he suggested that general relativity predicted that gravity itself would move across the universe, and that if you could detect that gravity, you might be able to say something about the objects that's creating it. And we call those signals gravitational waves. This is a movie I like to show from my colleagues at Goddard. It's different than the movie you typically see, which shows a kind of flat rippled sheet with waves spreading out from the center like waves on a pond. But I like this movie a bit better because it emphasizes the most important thing about gravitational waves, which is when a source generates gravitational waves, those gravitational waves move outward in every direction in the universe, which is why you can do astronomy with them. Just like a star gives off light, and it throws off light to the left, and light to the right, and light up and down, and forward and back, and in every direction, the emission of gravitational waves by strongly gravitating systems is exactly the same. It goes in every direction, so no matter where we are, we can gather those gravitational waves, detect those gravitational waves, to say something about what was creating them. Now, the movie you're watching is of two black holes orbiting around each other and slowly spiraling together. We'll come back to this at the end of the talk. The bright lines you see are places where the gravitational waves are strong. The dim space between them are places where the gravitational waves are weak, and they move outward from the gravitational waves out into the universe. The pattern is not symmetrical. There's information in that. It tells us something about the orbits of the black holes. But eventually they merge together and form a new black hole. And when that happens, all the gravitational waves disappear. They end.
Why do you say it's not symmetrical?
If you'll notice here, there is a very definite axis where they go more strongly this direction than this direction.
Thank you.
Okay?
How do you define gravitation?
It's around the axis of rotation. Yeah, it's defined by the orbit. Sorry. Someone? Sorry, I missed.
How do you define gravitational waves?
So the question is, how do I define gravitational waves? So actually, this is a good place as any to do this. So when you were first taught about gravity, you were taught that gravity depends on two things. The strength of gravity depends on the mass of the object creating the gravitational force, and it depends on how far away you are from the source. Okay, so in this room right now, your neighbor is emitting an enormous amount of gravitational force on you compared to me because she's much closer to you. But the Earth is dominating both of us because it's enormously much more massive than you. Okay? Okay, so let's imagine these two black holes. Let's just start from one. I have a black hole here, and it's emitting some gravitational force on the universe around it. And you feel that force on your forehead pulling directly towards the black hole. Okay? And if I move, you feel the force follow the black hole. And in particular, if I come closer, that force on your forehead gets stronger. And if I get farther away, that force on your forehead gets weaker. Okay? Now, it's an extraordinarily weak force. In fact, Einstein realized very rapidly that this was going to be very weak, and he thought we would never have the technology to detect it. Okay, 100 years later, haha, joke's on you, Al. Okay, but, okay, imagine two of them. This one's pulling on your forehead, and this one's pulling on your forehead. And if they move, just like in the movie, like in an orbit, this one's closer and pulling on your forehead more strongly. This one's farther away and pulling on your forehead more weakly. And so if you just close your eyes and measure the force on your forehead, it goes up and down as those two black holes go around each other. And that's what we're measuring when we say we're measuring gravitational waves. Now, what are they? We'll come back to that. Okay, that melts your brain. Question over here. Yes, sir.
When these black holes merge, you're showing this picture. It looks like there's field lines there, but it just...
Yeah, so right at the very end, there are still waves around the black holes. They're very weak.
Yeah.
They are just like the sound waves you get off a bell when you ping it with a hammer.
It's resonating.
It's resonating, but that will eventually settle down.
Yeah, it'll decay to zero.
It'll decay to zero. Okay? Is everyone good? Okay. So, as I said, Einstein thought we would never have the technology to do this. Okay? But, as it turns out, Einstein invented a lot of the physics that led to the technology of today. And we have supercomputers and lasers and superconductors and material science and all kinds of technology that we can use to make these signals so extraordinarily tiny that Einstein thought they were impossible to detect, detectable. And we've harnessed all of that technology together, and we've built two great machines called LIGO. This one's very near here. This is in Hanford, Washington. It's just a couple hours north of where I grew up in Eastern Oregon. It's on the edge of the Hanford Nuclear Reservation. If you fly into Tri-Cities and you're watching out the right side of the window as you go in, you can see it. If you never fly into Tri-Cities and you go to Google Satellite, you can see it in the satellite image. Okay. This one is in Livingston, Louisiana. Okay, so it's northeast of Baton Rouge. It's out in the southern pine forest there, and you can also see it on satellite if you go look. The environments are very different, which means we have very different problems depending on which detector you live at. Okay, so here, does anyone know what that is next to the arm there?
Interferometer.
Well, this is an interferometer, but what's right next to it? That's water, right? Because it's a swamp in Louisiana. And to build the instrument, we had to dig up dirt to make a mound to build the interferometer on. And when you have standing water in Louisiana, you also have alligators. Right, okay. So there's you know, the undergraduates usually come back, but there's alligators and stuff out there. This is on the Hanford Reservation, okay? So in eastern Washington, right, we have lots of, it's high desert, so we have lots of tumbleweeds blowing across the landscape. And they bundle up against the side of the interferometer there. And that causes noise that we have to deal with, so we have to gather them up. But they come from the nuclear reservation, so they have to be disposed of as if they're nuclear waste, right? So we have different problems depending on which one of these two sites you're at, okay? Okay. This is what inside the interferometers look like. This is our so-called input optics. And this is where the magic of gravitational wave detection happens. That big piece of glass you see there is about 40 kilograms. It's about this big across. It looks like a giant coffee can hanging on its side. Okay, it's made out of fused silica. It's transparent to visible light, but you'll notice it has this kind of purple and green haze. It's actually not transparent to infrared light, which is the light that we use in our lasers. Okay, so this is our kind of Death Star picture, but we have this giant laser that lives in the corner of the building here, and we shine it down these two arms, okay? So from the building all the way to the end of the arm is 4 kilometers, about 2.5 miles. Okay, and so here and here, there are mirrors, basically, very similar to that input optic right there. And so what are we doing? We shine the laser down that arm, it hits that mirror, and it comes back, and I time how long that takes. Okay? Now, you asked, what are gravitational waves? So we talked about what they were. The question is, what do they do to an experiment? Because if you build an experiment, you got to look for something you can measure. So that story I told about the force they exert, if a gravitational wave comes through LIGO, what it does is it stretches those arms. It changes the distance between the building and the mirror at the far end, and it stretches it so that the laser has to travel farther than it did to start with. So it takes the laser longer to go from the corner of the building out to the arm, to the end of the arm, and back again. Now, at the exact same time, the reason we have 2 arms is the other arm gets shorter. And so the laser that goes down that arm comes back early. And that's what we look for, right? The arms are kind of changing lengths all the time because, you know, people are bouncing basketballs and trucks are driving by and there's tumbleweeds we haven't cleared out, okay? But when the arms do this in unison, one gets long and one gets short. And then this one gets long and this gets short. And back and forth, back and forth, back and forth. That's the signature of a gravitational wave. Okay? You see this? This is called the gravitational wave dance. I want to see you all doing it in the line dance at the bars next week.
Would the gravitational waves affect the velocity of propagation of the light down there?
Okay, so you've asked a very hard question, and the answer is no. The question is, will the gravitational waves affect the speed that the light propagates at? Okay, and the answer is no, because light propagates at the same speed for all observers.
Not affected by gravity.
Okay, so gravity does affect light, but it does things like it redshifts the light. It changes its energy. It does not change its speed.
Changes its frequency.
It changes its frequency. Okay?
Okay.
Okay, we can talk about that at the end.
Yeah.
Okay, so this is the game. Sorry.
Can the waves go in reverse?
Can you ask me that slightly differently? I'm not sure what you mean.
Or do they always go in the same direction?
So the waves propagate along straight lines from whatever created them to LIGO. So if there is a black hole system up here, it'll go through LIGO, it'll make a signal. If there's a black hole signal over here, it'll go through LIGO sideways and make a signal. If there's one down here, it'll go through LIGO and make a signal. Now we use that fact. This is why we have two of them. Okay, there's one in Livingston and one in Hanford. The way we point with LIGO is the gravitational waves hit one of them first, and then it hits the other one. And based on that timing, we're like, they came from over there. Okay, so they can go through it any direction. Gravitational waves are not like telescopes. They don't point. They're more like your ears. No matter where I stand in this room, if you close your eyes, you can be like, yeah, I think he's over there. Gravitational waves are the same way. No matter where they are, we can say they came from over there. Does that help? Okay. Okay, one more.
What kind of time bases do you use to synchronize the two?
This is all done with GPS.
Okay.
It's all done at nanosecond, a little bit more than nanosecond precision, but it's done with GPS timing. Yep. Okay? Okay, one more.
Are they the same orientation?
So they do not have to be, but the two LIGOs were chosen to be because they were the first detector we built. And there was skepticism on some physicists' part that we would be able to detect them if they were not co-aligned. They are not perfectly co-aligned because of the curvature of the Earth, but they're as co-aligned as they can be. Okay? Okay. Okay. Now, as John said in the introduction, I also work on building one of the, this is what LIGO looks like built out of Lego. So I show this at LEGO conventions, and they're like, it's really not a very good model. And I'm like, and they're like, oh my gosh, it looks just like the real thing, right? So, okay. I also work on building one of these games, one of these observatories in space. So,
are you going to
sorry.
actually describe the detector and all of that sometime later in the talk?
This is as much as I'm going to tell you.
About that?
Yeah. Do you want to know more about it?
What are we actually looking at there? I mean, you said it briefly, but...
So this is the aerial view of LIGO. The building here is where all of the experiment is, and the lasers and the instrumentation. And then these arms, they're 4 kilometers long. They're concrete tubes about this big, and inside is a 1 meter diameter spiral welded steel tube that's had all the air sucked out of it. And that's all there is.
Okay, I'm talking about the detector, though. What is actually, how do you measure the difference in the...
in the arm lengths? Yeah. So for those of you who remember your physics classes, we use interferometry to do this. And so what we do is we set the detector up so that the laser beams go back and arrive, and when we interfere them, we set them up so that the light exactly cancels out. Okay, so that's called destructive interference for those of you who remember your wave physics. Okay, and what happens is when one of the arms gets longer, those waves don't match up perfectly, and so you get, as we say, light leaking out of the detector. So that's how the detection mechanism works. We describe this measurement in terms of a timing experiment because that's physically what changes the arrival of the wavefronts of the laser when it gets back. So, is that what you were after?
Yeah, more or less. And then,
okay.
Yeah, that's helpful. And then the mirrors and the lenses that we're looking at there are just part of that detector system.
Yeah, so in fact, these mirrors, all the lasers are suspended on pendulums. And in fact, they're suspended on 4 linked pendulums to prevent ground motion from keeping them, to keep them still. Yeah. Okay?
All right.
Okay. You good?
Fraction of the size of a proton.
Fraction of the size of 1/1000th the diameter of a proton. Yeah. Okay. I'll show you that in a minute. Okay. Everyone good? Okay. So we're going to do this in space. Okay. So this observatory is called LISA, the Laser Interferometer Space Antenna. As John said, it's a detector that is still in the future. One of the things you get used to in this game is that big science takes big amounts of time and big amounts of money. Okay, so the Hubble Space Telescope took 20 years to build from its inception to the time it flew, and LISA's kind of on that sort of time scale. But right now, 2030-ish is the target launch date. It consists of 3 individual spacecraft. Each one's about 2 meters across, has a big solar shield that faces the sun, and deep inside the spacecraft, it has a telescope that shoots the laser out to the distant spacecraft and receives the laser from the distant spacecraft. And the difference is the distance between 2 spacecraft is about 1,000,000 times larger than the distance for LIGO. It's 5 million kilometers between spacecraft, about 16 seconds for the laser to fly back and forth. Now, on the LISA spacecraft, we have mirrors. Oh, this is LISA built out of Lego. On the spacecraft, we have mirrors. So these are what our mirrors look like. When you put mirrors in space, you just let them float, and you don't have anything touch them. So that all they do is they move when gravity pushes them around, because that's what we're trying to measure. They're made out of gold and platinum, so they're very shiny. They reflect the laser light. Okay, and they weigh about 4 kilos each. It's about 4 centimeters across, sorry, about 2 kilos each. Okay, it's about 4 centimeters across there. Now, as you might imagine, they don't let people like me and you hold the gold and platinum cubes, because they cost like 40 million euros each. Okay, but my friends at NASA made me one out of tungsten. Okay, because tungsten has the same density, about 98% the density of the gold and platinum alloy that we use in the real ones. So that cube I'm holding right there is life size and life weight of the real one that we're going to fly on LISA. Okay, and in fact, we flew 2 of them on a mission called LISA Pathfinder in December of 2015 to prove that we could use this technology in space to detect gravitational waves. Okay? I brought that cube with me. Do y'all want to hold it? Yeah, you do. Okay. So, no, they don't let me touch that one. The first time they handed it to me, I licked it, and they never let me touch it again. No, I'm teasing. Okay, so here's the cube. Okay, so I'll pass it around. Okay, you know, like 6,000 people have held the cube. Okay, so I should have polished it before I came. I'm sorry, I was trapped on a plane. It was in my luggage. Okay, I only have one rule about the cube.
You want it back?
I have 2 rules about the cube. I want it back. My other rule is don't hurt yourself. Okay? You're welcome to take a picture, balance it on your head, do whatever you want. Don't hurt yourself with it. It weighs 2 kilos. Yeah. Okay? Okay. So I'll pass that around, and y'all can look at it. Did I see a hand back there? Yes.
So in that future spacecraft, how many of those things will be in one?
Yeah, the question is how many of those will be in LISA? So there will be 2 in each LISA spacecraft. So there'll be a total of 6. Okay, so there's 2 telescopes on each LISA spacecraft, and at the heart of each telescope is one of these cubes.
What's the size of the gold platinum?
The size of the one you're holding. That's 1 to 1.
Really?
Yeah, cool, huh? So you'll notice these little divots. Okay, so when you hold it, you'll feel how heavy. You can't just put this in a rocket and throw the rocket into space, right? It'll destroy your rocket. So we clamp down on it. We call that caging. We fly into space, and when we get to where we're supposed to go, these 2 fingers push it out into the middle of the spacecraft, and then they pull back and leave it floating.
Is there any station keeping required?
We do what the cube tells us to do. So the spacecraft has station keeping, but it moves to follow the cube.
Cube
Yeah.
floats,
The cube and the spacecraft follows. Yeah. Okay? Okay. Other questions about LISA?
What kind of orbit is it in?
LISA will be in a Earth-trailing orbit, so it will follow the Earth around the sun. It's about 20 degrees behind the Earth. So I didn't see who asked that question. Sorry. Okay? So 2030, I'll come back and tell you about the first discoveries about LISA. I'll be back before then, I'm sure. Okay.
Now, the major difference in terms of what LISA is going to be able to detect, you might want to talk about that.
Yeah, so LISA and LIGO will see very similar things, with the exception that LISA can see things that are much more widely separated than the things LIGO can see. So there are things that they both can see and see equally well, some things that only LISA can see, and some things that only LIGO can see. Okay, so we can talk about those differences, but I'm going to tell you about the LIGO discoveries. But as part of that, I'll tell you how LISA would be able to observe them as well. okay? But if you want to ask that at the end, I'll come back to that because that's a longer conversation than I have right now. Okay. Okay, you good?
Gravitational waves from inflation.
LIGO and LISA may both be able to see gravitational waves from inflation if they're stronger than standard theory predicts. And we don't know whether or not that's true or not. So, okay. And we can have a long conversation about that if you want to. So, okay.
Shane,
Sorry,
Shane,
I'm hearing a question. Yes, ma'am.
who came up with this idea?
For LISA?
For Lisa, yeah.
If you ask almost any of us, we will tell you it was my colleague Pete Bender at Gila in Colorado. He was really the earliest proponent of this. Ray Weiss, who's a colleague of mine at MIT, Ray just won the Nobel Prize for the first detection of gravitational waves. So Ray is the first person to think about doing interferometry, what these instruments are called. But to do it in space, most of us will tell you it was Pete. Yeah. But Ray, I mean, Ray thought of everything years before any of us did, so yeah. Okay? Okay. So I've told you about the instruments, but the question over here was about, well, what can LIGO and LISA see differently? This is ultimately the question, right? If we're engineers, this is great fun. We love building awesome instruments that do impossible things. But if you're an astronomer, you want to use this to understand the universe. So what can you see? Well, what you can observe is anything where you have big amounts of mass moving in dynamical ways. Stars going around each other in orbits, stars exploding, supermassive black holes merging in the centers of galaxies, okay? Possibly gravitational waves from inflation, from the Big Bang, when all the mass was being thrown out into the universe. Any situation where you have large amounts of mass moving around will generate gravitational waves. And our job as astronomers, our job as the new astronomers, is to learn how to interpret those signals to tell you what it was that's throwing those gravitational waves out into the universe.
But
Okay?
just a star sitting all by itself.
Will not generate any gravitational waves.
Okay.
Yes, absolutely. It has to be moving in some dynamical way. Okay? Accelerating, for those of you who remember your physics.
Okay.
Okay? Okay. Now, part of the story here is that if ordinary matter generates gravitational waves, atoms, it also has the opportunity to generate light. And there's very special things you can do if you can detect something with both light and gravitational waves together. Okay? Okay. So, I'm going to tell you about our 8th gravitational wave detection. Every gravitational wave source that we've detected has a name. Okay? It has a weird phone number, kind of like this. GW means we detected in gravitational waves. The first 2 digits are the year, the month, and the day. So that was 2017, August 17th. Now, what was happening in August of 2017? We were all sitting around waiting for the total solar eclipse. Okay, I was in Casper. How many of you saw it?
Oh, yeah.
Yeah, right? And it was awesome, right? Yeah, okay. So, I was giving this talk, the version of this talk, in Casper on August 17th. And that morning when I got up, I knew the story I was about to tell you, that I'm about to tell you now. But I had to keep it secret during that talk. So everyone just thought I was really excited because of the eclipse, right? Now, as one of my friends said, only a gravitational wave discovery can make a total solar eclipse the second most interesting thing in astronomy. Okay, the eclipse was awesome, but this story I'm about to tell you literally, not even with any semblance of exaggeration, transformed the way we do astronomy. There is no discovery in astronomy nearly as important as this in the last 100 years. It's as important as the discovery of the expansion of the universe. It's as important as the discovery as the cosmic microwave background. This discovery transforms the way we do astronomy in the modern era. Okay? So what happened? I've forgotten the time now. I should have looked it up before I came. Early in the morning. It was like 5 or 6. A signal was detected in the LIGO detectors. I'll show you that signal in a moment. Okay? Now, that's not unusual. At this point, we've made like 7 or 8 detections. But based on the detection, we knew it wasn't a pair of black holes, which was the only thing we had detected up to this point. It has a slightly different character, which I'll show you in a moment, and we knew immediately it was something new and different. Now, one of my colleagues, Tyson Littenberg, who was a postdoc at Northwestern with us, now works at Marshall Space Flight Center. And he works on LIGO still, but he works on an experiment called Fermi, which is a gamma ray telescope. And Tyson noticed that 1.7 seconds after the LIGO signal, Fermi also detected a signal. And he sent an email around that said, hey everybody, did you notice this? And the entire astronomical community in the world melted down. Okay? Literally. Okay, so the next 10 hours were the 10 most intense hours in the history of astronomy, because every observational astronomer on the planet was waiting for LIGO to tell them where to point their telescopes. Because we had detected a signal in gravitational waves, and the one telescope that was looking at that moment, Fermi, had detected light, in this case gamma ray light, something we call a gamma ray burst. Okay? And so every telescope on the planet wanted to point in that direction to see if they could see what we call the afterglow. Okay? So let me show you the data, and then I'll show you what we found. So this is what LIGO looks at all the time. Okay, this is what we call a chirp. This particular display is what we call a spectrogram. Okay, and so spectrogram is a fancy physics word, and the plot looks really technical, but many of us have seen spectrograms in our everyday life. Okay, so along the bottom here is time, and along the vertical axis is frequency. And the place where you've seen spectrograms before is on your stereo. So, okay, so your stereo's home, it's playing AC/DC or Bach or whatever it is you listen to. Okay, and it's got those little lights that go up and down all the time, right? Okay, what those lights are telling you is how much of the signal sounds bass sound, how much of the signal is treble or high-pitched sound, and how much of the signal is in the midtones. Okay, and so this plot, as you go across, this tells you if it's bright, it says there's a lot of the signal that was treble tones, or if it's bright here, there's a lot of the signal that was midtones, and if it's bright here, there's a lot of the signal that's bass tones. And what you see is as the source evolves in time, initially there's a lot of bass, eventually there's some midtones, and eventually there's a lot of treble tones. So we call that a chirp. It's something that starts really low pitched and it ramps up and ends very high pitched. Okay? Now, you'll notice here this shows about 30 seconds. We can actually see this for about 100 seconds in the LIGO data. Okay. Right when it ended, this yellow line, this is what gamma ray data looks like. And this really clearly shows why I'm not a gamma ray astronomer. Right? Because all they do is they count how many gamma rays they've seen. They're like, oh yeah, 975, 950, 985, 980, 1020, blah, 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 blah. Yeah, this is the life of a gamma ray astronomer. Okay. They know I make fun of them. It's okay. Okay? But right here, the signal jumped up to over 1,500 gamma rays, and they flipped out. A gamma ray burst, an enormous surge in gamma rays compared to what they're used to looking at. And it happened in very close proximity to the LIGO event. And that was the thing that set us all off. Okay? So what does all of this mean? This long signal from LIGO tells us that we're not looking at black holes. It tells us we're looking at something called a neutron star, which is a very specific kind of stellar skeleton. Okay? The fact that there's a gamma ray burst immediately at the same time as the gravitational wave signal confirms something we've speculated for about 20 years, which is gamma ray bursts, this particular kind, we call them short gamma ray bursts, are created by neutron stars. We've never been able to prove that. And here, in just 100 seconds, it seems like we proved it. And indeed we did. Okay? So what's a neutron star? A neutron star is a skeleton of a dead star. When a massive star reaches the end of its life, it collapses and explodes. If it's really, really heavy, it will create a black hole. If it's not really, really heavy, just kind of really, really heavy, it will create something called a neutron star, which is about 1.5 times the mass of the sun, squeezed down to something that's just 20 kilometers across. Okay? So here's a map of the valley around Jackson. And if I plopped a neutron star down on top of us, this is how big it would be. The space you can drive in 10 minutes in the summer, maybe 3 hours right now, okay? You squeeze everything in the solar system, the sun, the planets, the asteroids, the comets, everything, and half of another solar system down together into this compressed object that we call a neutron star. Now, if you read about astronomy, you hear about these things all the time. I'm telling you about them. And I'm just be like, oh yeah, neutron star. Okay? But these are the extreme exotic objects. The gravity on the surface of a neutron star is 2 billion times stronger than the gravity here on the surface of Earth. If you were walking across the surface of a neutron star, and you could barely walk across it, but imagine you could, and you had the misfortune of coming across a cliff just 1 millimeter high and fell off, by the time you reached the bottom of that 1 millimeter high cliff, you would be traveling at 30,000 miles per hour. These are weird things, which is why it's so awesome that we can detect them and understand them with this kind of astronomy. Because there's no way you can simulate this in a laboratory on Earth. Here's a picture that we released. This was done by one of my artists colleagues in our marketing division at Northwestern, showing the neutron star hanging over the skyline of Chicago. If you could stand on top of the Willis Tower, Sears Tower, for those of you who don't remember that it was changed to Willis, and reach up with a spoon and grab just a tablespoonful of material off of the surface of the neutron star, the mass of that sugar cube-sized bit would weigh 30 times more than the entire mass of every man, woman, and child on Earth. These are exotic objects. Now, I was giving this talk a couple months ago, and someone pointed out and said, yeah, but wouldn't there be some extreme gravity effects if this was hanging over the city of Chicago? It's like, yeah, you should totally see like investment bankers and people just flying up into the neutron star. So, okay. But these are exotic objects, okay? And this event provided us one of the most remarkable opportunities to study them. Let me show you a movie of the event from start to finish. This is an artist's rendition, not unlike the one that we talked about at the beginning. When LIGO first detected the 2 neutron stars, they were going around each other about once every 10 times a second. Okay? They were separated by about 400 kilometers. And what you see is the gravitational waves being shed off of the neutron star in every direction. Those gravitational waves carry away energy. And what that does is it makes the orbit shrink. And so as the orbit shrinks, the neutron stars get closer and closer together, which makes them go faster. And as they get closer, the gravity gets stronger, so the gravitational waves get stronger. Eventually, they see each other and they begin to distort, and then they merge. And at the moment they merge, they explode. And that's the gamma ray burst. You see this enormous jet surging off into the cosmos. And the shattered remains that are left behind are in this ever-expanding cloud of debris. We call that the kilonova. It is material that was once at nuclear density. It is spreading outward and recombining to form heavy elements. Okay? If you read the news about this, they'll tell you this is where gold and platinum and stuff like that came from. So you can make Lisa cubes, right? Okay? Over time, the gamma ray burst impinges on the area around it, and the kilonova begins to fade and cool. So we started with gamma rays, it faded into X-rays, it faded into visible light, it faded into radio waves, and it is still in fact visible today. Okay? Our radio astronomer friends are the only ones right now who can see it, but they are still observing it. But eventually, this will fade away, and then there will be nothing left for us to see at this point in the sky. Okay? Now, remember we said for 10 hours every astronomer on the planet wanted to see this? Well, as it turns out, 10 hours later, they discovered it. So this galaxy right here is called NGC 4993, okay? And right there, on the side of it, is the kilonova. Okay? So we watched that. 70 telescopes around the world watched it for 3 weeks until it went behind the sun. When it came out from behind the sun, our X-ray astronomers and our radio astronomers were the only ones who could see it. The paper that we wrote about this has 4,000 professional astronomers on it. 2/3 of the world's professional astronomical community is on that paper. Okay? It's the largest paper ever written in astronomy. Okay. Amateur astronomers, if they had known about it, could indeed see this. This is my telescope. This is Cosmos Mariner. For those of you who are amateur astronomers, this is the place in the sky. It's right on the border between Corvus and Hydra there. This galaxy is in the NGC catalog. I went back and looked at my notes. I've seen that galaxy. My notes say dim fuzzy blob. So I was unimpressed by it, okay? But I'm going to go back and look at it now because I want to see it again, okay? But anyways, but you can't see that galaxy. It is there in the sky. And amateur astronomers have tried to follow up on it, but we can't see the, we got to it too late. We couldn't see the globe, but we can see the galaxy. Okay, let's wrap up here towards the end. So the last thing I want to do is I want to talk to you about how we represent signals. You've probably been listening to me talk about seeing the gravitational waves or hearing the gravitational waves. And what's hiding in that language is the fact that we don't have any way of describing what it is that we're doing that meshes on to our normal sensory way of describing the world. Ordinary astronomy is done with telescopes, which are like bionic eyes. They're machines that are designed to do something your body already knew how to do. But gravitational wave detection is not that way. There is no gravitational wave detector built biologically into your elbow, right? Physicists for 50 years argued about whether or not they were real because we didn't have any way to understand physically what they do to the world and how we might sense or detect them. And so we struggle with how to present gravitational waves to people because this is what our data looks like. Okay? And when we make a big discovery, I send this to the editor at the Chicago Tribune. And they're like, go away, kid, you bother us. Because they want pictures from Hubble, right? We all grew up looking through Hubble. And this is not exciting for the readers of the Chicago Tribune. So what do we do? Well, as it turns out, LIGO signals are waves. And waves are waves are waves. We describe all waves exactly the same, whether they're gravitational waves, or light waves, or waves on a pond, or, as it turns out, audio waves. They're characterized by 3 numbers: a wavelength, an amplitude, and a frequency. And the LIGO signals happen to have frequencies that are exactly the same as the frequencies your ear can hear. So, if I steal your iPhone and replace all your Katy Perry or all your Glenn Miller Band or whatever it is you listen to with these wiggles, when you go to play your music, you'll hear gravitational wave data instead. You'll hear the gravitational waves transformed into sound in a way that your body can experience. Okay? So I did that. I'm going to play you a couple, and then we'll call it a night. Okay? Okay. Now, I will tell you, I just have this on my iPod directly, and it spins up all the time. And my 12-year-old's like, really, Dad? Okay. But I'm like, it's the music of the cosmos, hon. It's okay. Okay. So these signals up here are black holes, and the neutron star signal is here at the end. So what I'm going to do is I'm going to play you the first black holes we detected. and then I'll play you the neutron star, just so you can hear the difference. And the reason for that is I want you to understand that there's real astronomical information in the signals. And you, even though you don't have a PhD in gravitational wave physics, you can hear the difference just by listening to it. Okay? So let's do the black holes first. So this is what the black hole data looks like. This is one of those spectrograms, just plotted slightly differently. It's a movie. You'll notice it spans only half a second. Okay, so that's the first difference between black holes and neutron stars. Black hole signals, very short. Neutron star signals, very long. As the movie plays, over here, when it starts, you're going to hear. That's noise. It's static. What you're used to on your radio when you're not on the station, on the TV set in the days when we had static on TV sets. Okay? No more. When it gets over here, you'll hear the signal come up out of the noise, and it'll be that chirp. Okay? It'll play twice. Once at the actual audio frequencies that it's at. It'll sound like a heartbeat. And then the second time, it'll play at a slightly higher frequency. So I push it up about 2 octaves on the piano just so you can hear it a little bit easier. But it's still the same data. It's just played a couple octaves higher. Okay? So here's what they sound like. Bump. Thump. Okay? That's what black holes do. And if I played all of these black holes, they all sound kind of the same. But if you listen to them on really good headphones, you can kind of hear that they're different. It's kind of cool. Okay? Now, the neutron star, I said, was in the LIGO Data for 100 seconds. Okay? And it's playing right now. I'm going to play about 50 seconds of it for you. Okay? Do you hear it? Yeah, it's way down there. Okay? The neutron stars are about 1/10 as heavy as the black holes. Okay, and in fact, the first black hole I played for you was this. The neutron stars are 1/30 the mass of them. So the black hole I just played for you was 30 times the mass of the sun. Okay, this neutron star is 1.5 times the mass of the sun. So the gravitational waves initially are very, very weak. Okay, and as they spiral together, though, what happens to the strength of gravity? It gets stronger, and as it gets stronger, you can hear it. Can you hear it now? Yeah. Okay. Okay. Now that chirp happens when the black holes become one or when the neutron stars collide and destroy themselves. And at that moment, the gravitational wave date is over. Okay?
So the neutron stars don't create a new neutron star, you're saying?
That is a matter of much debate. Most of my colleagues will tell you that they formed a new black hole, but since it's only one, it's not making gravitational waves. But I have a standard bet of a bag of jelly donuts and a Dr. Pepper that's a hypermassive neutron star. And I have reasons, but mostly just to be contrary. So, okay. Okay. So let me taper off here. So this is, oh, I should have updated this plot. There are 4 black holes missing from this plot. You knew that though, right? So, okay. This shows the current state of affairs in our understanding of massive dead objects that you can see with gravitational waves. Every one of these blue objects up here is a pair of black holes detected by LIGO, okay, that merge to form a new 3rd black hole. And then down here at the bottom, these 2 orange dots are the neutron star, and the question mark is we don't know what it is. This plot I like to show because it hides one of the greatest mysteries we have in astrophysics right now, which is this thing right here. We have never seen a black hole lighter than 5 solar masses. How come? Does nature forbid them? Does our instruments suck at detecting them? We don't know. Similarly, we have never seen a neutron star heavier than about 2 solar masses. How come? Does nature forbid them? Or are we just not good at detecting them? We don't know. But you'll notice 170817, whatever it became, lies squarely in the mass gap right here. So this is why we are desperate to know what it is, because we would like to know what's in the mass gap. Okay, yes, sir.
Are these assumptions on what you might apply by physics or something as to what the mass of the combined object would be?
Yeah. So
There's our conservation of mass here?
So the question is how are these masses assigned? So we actually measure the masses in all of these systems to some level of accuracy. Okay? This image is actually generated by a tool we have at Northwestern. It's on the web. If you go to our website at CIERA, it will let you play around with this, and you can turn on the error bars and see how accurately we know all those masses. Okay? But these are all measured masses. Okay? Okay. So this is the game. This is the absolute frontier of astronomy today. Okay? Now, people always ask me, is it awesome to live through it? Yeah, of course it's awesome to live through it. Was it fun? Yeah, it was great, except we didn't sleep much, okay? And my email is out of control. I'm currently at inbox infinity, right? Okay, but people always ask, what's the most important thing about this? And the most important thing about this is that what you've just heard was not accomplished by a single person. LIGO is an endeavor that involves thousands and thousands of scientists around the world, but also tens of thousands of people who aren't scientists. We had to have an army of welders spiral weld those 4-kilometer, 1-meter diameter beam tubes. The guys from the Chicago Bridge and Iron Works came out and did it. We had construction engineers who had to build the LIGO facilities. And we had to teach them a lot about lasers. Because when they build one building with their plumb bob, 4 kilometers away, you can't build that building with the plumb bob because the Earth is curved. And the laser knows it. Right? So LIGO is this awesome mix of people who are technical scientists and people who aren't. But we're all engaged in the same game for the same reason, and we all have to be able to talk to each other and understand each other and know why we care about the things we care about. And it took literally tens of thousands of people like me and tens of thousands of people just like all y'all. And the truth is, the only people who get on the papers are people like me. But we couldn't do it without all the folks like you as well. And that's the true legacy of LIGO. Of any big science project, whether it's Hubble, the LHC, LIGO, LISA, anything you want to talk about, is there are always a gazillion people behind the scenes making it happen besides just us. So don't forget it, okay? Okay, I always like to leave you with more to go read and learn on your own. There are books appearing about gravitational waves, and I haven't read them yet, so I haven't put them on the list, okay? But these are the ones that I know about. This is probably the best public level book about relativity, gravitational waves, black holes, wormholes, all of that stuff. It's by Kip Thorne. Kip was my postdoc advisor when I was at Caltech.
Kip was what?
My postdoc advisor when I was at Caltech. Okay. He was also the Nobel Prize winner with Ray and Barry. Yeah. Yeah, those guys, okay? But this book is great. It has a good chapter on gravitational waves, but it has lots of stuff about black holes and wormholes and all of that sort of stuff. Marcia is a very gifted science writer at MIT. She's written a lot of history books. Her most recent one, some of you may have read, called The Day We Discovered the Universe. It's about the discovery of the expansion of the universe. But this is her book about Einstein's, about gravitational wave detection. It's called Einstein's Unfinished Symphony. It was written before LIGO was completed. Okay, so if you go to the library, that's plausibly the one they have there, but she just put out a new edition post-discovery. Okay, so if you get the post-discovery version, there will be a chapter in there about the first detection of gravitational waves. If you would like to help us, this is a citizen science project called Gravity Spy. There are things that you absolutely cannot teach a computer to do. In particular, you cannot teach it how to read spectrograms effectively. So we have a project, because I can teach you how to read spectrograms effectively. We have a project where you just log on to gravityspy.org with your phone, your web browser. We show you a spectrogram, and you tell me what it is. Okay? There's several different types. You tell me what it is, and I show you another one. You tell me what it is, and I show you another one. And you tell me what it is, and I show you another one. And then we take those to the computer and we say, see? These, not these. Okay, and it's working. Okay, so we have about 20,000 people who have done this with us. They range in age from about 5 to 95. They have done 1.4 million spectrogram classifications. We would love you to participate with us. Okay, so if you're interested, please go. Here's a link to a set of, there's my blog. That link there, that second link is to a 14 series post that starts from Newtonian gravity, the way we were talking about pulling on your forehead, and ends with gravitational waves. There's a set of videos that go with that talk. They're little 4-minute videos that you can read and melt your brain with and then think about a little bit. And then these last 2 links are to LIGO sites, so you can get the sounds that you just heard me play. You can go see our movies like the simulation I just saw you, things like that. Okay? Okay, I have said everything I'm going to say. So thank you for your attention, everybody. I'm happy to take questions for as long as we want.
Questions for Shane?
Okay, yes, ma'am.
Is it true that it's because of gravitational wave that they were able to detect the Higgs boson? Is that?
So the question is,
It provided evidence.
is there a relationship between gravitational waves and Higgs boson? So I would say no. Okay, with the following caveat. So there's a lot of cross technology between the LHC and LIGO, and all big sciences this way. We use the same detectors, we use the same computers, we use the same data science techniques, all of that. From the physics side, however, the Higgs boson is part of a very grand theory that describes all the matter in the universe called the Standard Model. It is the thing that tells us what quarks exist. It's the thing that tells us the electrons and another set of particles called the leptons exist and how they combine together. And the last missing particle in the Standard Model was the Higgs. The thing that's wrong with the Standard Model is that it describes every electrical phenomenon we've ever seen. It describes every magnetic phenomenon we've ever seen. It describes every nuclear phenomenon we've ever seen. It says nothing about gravity. So this is, in theoretical physics, the frontier is trying to mesh the Standard Model with gravity. Okay, and that's called the grand unified theory. That's what, so your friends who are string theorists, they will tell you, oh yeah, we know how to do this. And the rest of us are like, okay, well tell me the experiment to go tell me you did it. And so I would say that's still in the future. So 10 years from now, ask me the question again, we'll see.
Einstein spent the latter part of his
Einstein spent a tremendous amount of his life trying to do this, absolutely. And he couldn't do it, yeah. So, okay, here and then I'll come. Yes, sir.
Scaling up the dimensions from LIGO to LISA enables you to have much greater sensitivity of detection.
Okay, so the question, this was related to the question earlier. So roughly speaking, the size of your detector tells you how big a gravitational wave you can see. Okay, so LISA can see much longer wavelength gravitational waves than LIGO can. So what does that mean? If we're talking about light, that's like the difference between seeing blue light and red light. Blue light has short wavelengths, and red light has long wavelengths. Astrophysically, what does that mean? Well, in terms of the things we were just talking about, everything we've been talking about is basically about orbits. And so the difference between LIGO and LISA is LIGO can see orbits that are very short and very fast. LISA see orbits that are very wide and slow by gravitational wave standards, fast by Einstein standards. So LISA, the black holes that LIGO saw and the neutron stars that LIGO saw, LISA will see them when their orbits are about 1,000 seconds, about 15 minutes. Okay? And to go from a LISA orbit, a LISA detectable orbit of 15 minutes, to a LIGO detectable orbit of about 100 per second, takes about 10 years or longer. But there should be sources that we can see with LISA that will then evolve, and then ultimately we'll see them with LIGO.
I'm sorry, LISA detects shorter
longer, faster, bigger. LISA's big, so it detects big orbits.
Okay. How did you know where to look for the gamma ray burst in the universe?
So in fact, sorry, I forgot to mention this part of the story. So we have 2 LIGO detectors, but our colleagues in Europe have one called Virgo. And in fact, it took all 3 of them to locate that place on the sky to look. So that map I showed you that showed where it was on the sky next to my telescope, there were these long ellipses drawn. That was where we told the telescopes to go look. And so they all just started banging away inside those circles.
Is that because of time differences?
It's triangulation completely. Time difference between the 3 detectors.
Gotcha.
Okay? Okay, yes sir.
I'm going to ask you one about what he just said, but then I have another question. When you have the longer interferometer arms, and you can detect lower and lower frequencies, causing those frequencies will have lower gravitational pull relative to each other, so that there won't be as sensitive. Is that correct?
So the strength of gravitational waves depends actually on 3 things.
Yeah.
It depends on the masses, the distance, and the frequency. So you can make up for weak frequencies by increasing the mass or moving it closer. The truth is we have to disentangle that information the same way optical astronomers have to disentangle light. We have to juggle some parameters. And there are ways to do that.
The real question is, can you tell us a little bit about the pioneers in searching for gravity waves? I'm talking about Professor.
About Joe Weber? Yeah. Actually, let me see if I have a picture here. So if you go to the LIGO sites, I do. I do not. I thought I had a picture. Here, I'll show you this anyways. If you go to the LIGO sites, you can visit them. So there's a bit. They of course let me inside, as long as I promise not to touch anything. So you can see the big beam tubes here. Okay, these are the input optics. This is what the sign out in front of Hanford looks like. This is what our computers look like. But in the visitor center, they have the first gravitational wave detector ever built. Okay, so it was built by a guy named Joe Weber, who was at that time at the University of Maryland, but he was also at the University of California, Irvine. So I asked his widow, Virginia, this, and she's like, yeah, I don't know where he got that. I asked her, where did he get the aluminum for the detector I'm about to tell you about? And she's like, yeah, I don't know. But he had a cylinder of aluminum that's about 1.5 meters long and about 1 meter in diameter. Weighs about a ton, a little bit more than a ton. And his idea for a gravitational wave detector was to take that and balance it around its middle on a piano wire. Okay, and it's at the LIGO Visitor Center. There's one at both of them. So if you go to Louisiana or Hanford, you can see it and you can touch it, and it will rock back and forth on that piano. Okay, so what's the idea? The idea is that if a gravitational wave goes by, what does it do? It stretches things. So it will take that bar, as we call it, the gravitational wave bar, and stretch it, and then when it goes by, it'll let go, and the bar will snap back to where it goes and start ringing like a bell. So Joe's idea was to balance this around the node. Those of you who are guitar players, you know the node where you can fret your guitar and not damp the string out, right? Balance it around the node and just tape microphones around it and listen to see if there are some gravitational waves. Now, Joe famously detected some events. And he had 2 bars, and he detected coincident events. And the story of what happened thereafter is a tragic one. Scientists are not the most socially adept people in the world. And there was a lot of very personal attacks back and forth about the veracity of these things. And Joe ultimately became very defensive about this. And so I think my perspective as a professional, if you go back and you read his early papers about the detections, he did exactly what he was supposed to do. He made an observation, he published his results, he suggested what it might be. He did not, in those early papers, to my mind, declare that they were detections. But it rapidly developed, and it's a very difficult part of our history. There's a great book written about this. Oh, so you were there. Yes, so you know the game.
And it's a good story because he's trying to use an electromechanical system to detect something that's very faint.
Yep.
And he ran into noise problems.
Yep.
And then now step forward 3 decades. Now you can use laser interferometry,
Yep.
which gets around a lot of the problems that we have.
Yeah.
So now you can
Yeah. So there's actually a huge gravitational wave effort spawned by Joe's early efforts to build bars that were cryogenically cooled. And it was maybe just 10 years ago now, after LIGO was constructed, that they finally turned to this. So this is the moment.
Okay, I'm going to have to cut this
Late
off
60s.
here, but Shane will be at the Senior Center tomorrow. Another topic. Remind us of the title.
From the Big Bang to Jackson Hole.
Everything you
Cosmic biography.